Hi, everyone. I'm Mainak. I've been working with MNE-Python for over 10 years, and I'm going to sort of share my experience analyzing OPM-MEG data using MNE-Python at the Martinos Center. Let me begin with a very sort of short overview of typical MEG processing pipeline. Probably many of you are familiar with it, but doesn't hurt to repeat it. So in MNE-Python, we have these data structures which are inspired by the different stages of the pipeline. So when you load in the data, you have the so-called raw object, which is a continuous time series of number of channels times times. From the raw object, you extract parts of your time series, which are time locked to the trigger, and you construct epochs, which is number of channels, number of epochs times number of channels times number of times. And then you average these epochs into evoked responses, which are number of channels times time points. And this comprises what's known as sensor space analysis. And in MEG, people often go beyond sensor space analysis. What they do is they take these evoked response data, and from there, they apply some kind of inverse operator, and they construct source estimate to get what's known as source space analysis. So this is how people analyze data in MNE-Python. Now, in terms of how it is done concretely, I would import my MNE module. I would read in a FIF file by specifying the name of the file. I can specify some pre-processing, like what are the bad channels, how do I filter the data. You would usually low-pass filter it and apply some high-pass filter to remove artifacts. And then you can save it and manipulate it how you like. Then you can do some pre-processing if you like, and then you extract the epochs. It's all like a couple of lines of code. And then you average it to get evoked responses. So this is how you would do sensor space analysis in MNE-Python. And then from there, we started thinking, okay, what do you need to do if I need to analyze the data in OPM? So before I get into OPM, I think it's worth thinking for a minute what happens in MNE when you actually load the data. So MNE has readers which will help you read data from many different vendors and file formats. So we have around readers for 25 file formats. And then when you read it in, all the metadata from all these different vendors, they get concatenated and they form this dictionary, which is an info dictionary, which contains all the information that is related to the measurement. And this has been really, over the years, built for squid measurements. And I want you to pay attention to these two particular elements in our dictionary. One is what's called the dev head T, and the other is the proj, or the projection operators. And these are really specific to squid, and we need to start thinking about how do we do such things in squid MEG. So the info, by the way, can be inherited. So when you read it into the raw object, and from the raw object, you construct the epochs, and the info gets inherited as you churn through the different stages of your pipeline. Okay, when you load in some squid MEG data, you look at the data and it looks really nice. You see some cardiac events, in the data. So the data is pretty clean, but it's punctuated by some cardiac events. And you think that, oh, MEG data processing is really easy. But then if you actually turn off the projection operators, which is used when you visualize the data, you realize that, well, the MEG data is clean, but it's not that clean. So there is definitely some noise in the data, which is not obvious because you're just using the software, which does it under the hood for you. And if you look at the the power spectrum density before and after applying projection operators, so this is after applying projection operators, but in reality, your data looks like this, and it captures all kinds of environmental artifacts. For example, as Robert mentioned, there are vibrations in the rooms. We had this experience where we had to turn off the AC and one of the peaks went down. So you have to be really careful in that sense. But the SSP really, or the projection operators really take care of this. Now, what's happening behind the scenes of the projection operator? So what happens is when the Megan or Electa or any of these MEG vendors set up a system, they set up the projectors for you, and it's periodically updated. So you do an empty room measurement, and from that empty room measurement, you compute the projectors. And when you do a human subject measurement, then these projectors are added to the recorded FIF file. And when you read it into MNE, they get automatically read into the raw.info. And now in MNE, you're normally not even aware that this is happening, but you can actually explicitly apply this using functions and methods such as apply proj or using the flag proj. But if you're doing OPM-MEG measurements and you're just getting started, you can compute your own projection operator. We have functions that allow you to provide a raw file, and you can compute your own projection operator. And the nice thing about this approach is this formerly known as signal-space projection, is that you can decide what your noise is and what you want to project out. So your noise could be empty room noise. It could be the baseline period of your epochs. It could be epochs of eye blinks or cardiac events that you want to remove. But what's important is that when you do apply these SSP operators, you want to always visualize the data and interactively choose the projector, so you ensure that the signal is not removed. And so in MNE, many of the visualization functions, for example, if you do raw.plot or evoke.plot, you can interactively check what is the impact of adding this projector to my data. And you may choose, okay, maybe I'll use a couple of projector vectors or maybe more to remove the noise. Now, to remove background noise in OPM-MEG, there are some additional challenges, as Robert and others mentioned. Well, the sensor array can move, and the sensor array may be different for different subjects. So depending on the head shape and size, you may have different sensor arrays. So I just, while we were doing the analyzing the data for our experiments, I sort of decided to sort of list some of the considerations we had in mind when choosing the method. And it's still somewhat of an ongoing process, but I'm trying to show, how we are thinking from the user perspective. So we have certain criteria. So, okay, does it work without sensor locations? Because maybe we don't have time to actually get the sensor locations. Does it work with a few sensors? Sometimes people have constraints on the number of sensors. Maybe they have 10 sensors, maybe they have more. Do you require additional sensors for this method to work? Again, maybe number of sensors is a constraint. And does it require some additional measurement? Because you don't want to add more to your experiment time, especially when you're working with patients or children, etc. So if you look at the SSP method, the signal space projection method, which has been used in the past, you don't need to have the sensor locations, and it can work with relatively few sensors. But one issue is that you do need to make some additional measurement, for example, an empty room measurement, and you need some sort of measurement which will give you a model of the noise. You can regress out the reference sensors from your data, and this would be nice, but there is this challenge here that it does require additional sensors, and that can be a problem if you don't have a lot of sensors, and you want to make use of all your sensors as much as possible. And then there are other methods that have come up. So the SSS has already existed, so-called max filter that people know it by. It does need sensor locations, both the homogeneous field correction and the SSS, they need the sensor locations. I know that there's some new work ongoing about whether they can work with few sensors, so I put a question mark there. But it has the advantage that it does not need an additional measurement. So there are pros and cons to these different methods, and you need to think about this from when you're doing experiments. Quick, math thing, just the relationship between these different methods. So in the SSP method, you're modeling your signal as a sum of your measured signal as a sum of your signal of interest and some kind of noise, which you decompose using an SVD. And from there, you compute a projection operator, which you then apply to your data, and that gives you your signal of interest. When you do the signal space separation method, you try to separate it out in terms of an inner and outer basis functions. And there, what happens is you try to estimate the coefficients of these basis functions, and then you zero out the coefficients of the outer basis, and that gives you the final field that the signal of interest. Now, I wanted to show you this because it is true that the signal space separation method and the signal space projection are quite different in many ways, but they're also similar in the sense that you're doing a matrix vector dot product. And so you're trying to, in some ways, estimate the same thing. And similarly, in the homogeneous compensation, field compensation method, again, you have some kind of projection operator, but that is derived from the sensor location. So here you're trying to model your field as a sum of your signal and the homogeneous field. And I want to mention this because sometimes people get hung up a little bit about, okay, should I use this method or that method? And I think more than how many decibels of noise you're suppressing, what you want to, it should be guided by is practical constraints, how much time you have, how much money you have, etc. So I think really thinking practically about it and making it usable is important. Now, the other challenge that we faced in the OPMs is how do we get the sensor locations? There's something that people get tripped up a lot about, but really it's not that difficult. You have 3 different coordinate system, and when we think about MEG, you have the head coordinate system, which is defined by the Bayesian, LPA, RPA. So these are 3 standard anatomically defined points. You have the device coordinate system, which is the coordinate system in which you have the sensor array, and you have the MRI coordinate system, which is the coordinate system of your MRI. And what MNE does when you do source localization, it brings everything into head coordinates, and then everything works magically. So, because it brings everything into head coordinates, you need to bring everything from these 2 other coordinates to the head coordinates. So you have the device to head coordinate system, which is in the info, and the head to MRI coordinate system, which is also, the standard procedure to do this. Now, we already have ways of computing this device to this head to MRI coordinate system is by using so-called fiducials in the NeuroMag system. You have this kind of electromagnetic tracking system. What you do is during the experiment, 2 minutes, you're quickly digitizing these points, and then you get the transformation by aligning similar points. Now, what we did was we 3D printed our helmets, and for getting the device to head transformation, in our helmet, we put some index points, which were predetermined points. And by aligning these predetermined points with the fiducials, we are able to construct this transform. And then for our experiments, what we did was we digitized the 3 anatomically predetermined points. We had the additional index points. We saved this, and then we had these 3 orthogonal reference sensors. And we saved this information to different files. And we had these 3 different functions, one to add the channel locations from our predetermined FIF file, which had the sensor locations, one to get the transformation matrix between MRI and head, and the final one to get device to head transformation matrix. And once you have this set up, the rest of the M&E pipeline just works. And then we did some median nerve experiment, which I just presented this morning, so I'll just quickly go over it. We were able to co-register everything to the same space, and you can see that the data looks quite similar once you understand the coordinate system and pick sensors which are close to each other. Some practical tips or what the papers don't talk about, and this is my last slide. So one thing to remember is that OPM data is still MEG data. So initially, when we started making our helmets, we printed these really nice 3D helmet, and we saw this artifact, and we were like wondering what the hell is going on. And maybe some of you have already caught what the issue is. We had printed a black helmet, which is a pigment which is causing artifacts. And every time the person had a cardiac event, you would see this like bump in the signal. And then what we did is we reprinted this helmet, and now we're getting clean data. So, people talk about the differences between OPM and SPIT, but it's important to remember that it is still MEG data. So you need to treat it with respect, have a pristine environment when doing your experiments. Turnkey setups are the key to usability and reducing failure modes. Something like SSP, how it has worked in the past. It's not how many decibels of noise it's reducing, but it's turnkey. It just works out of the box, and you don't even realize it. And finally, I wanted to say that we have learned things the hard way, but we do want to share our lessons with the community, and I hope the rest of the community does the same, so we all make faster progress together. Thank you.